Splicing motor power wires in the control cabinet is permissible in certain scenarios. Adhering to electrical codes, standards, and best practices is essential. There are several permissible splice types. Firstly, soldered splices. Splicing wires using solder is a reliable method that provides a permanent electrical connection. Solder splices must be properly executed and protected with heat shrink tubing or solder sleeves. Secondly, crimped splices. Crimping wires together using insulated crimp connectors creates a secure and durable connection. Ensure that the crimp tool and connectors are appropriate for the wire size and type. Thirdly, twist-on connectors should not be used for power wiring connections due to concerns about loose connections and potential arcing. All splices must be properly insulated to prevent electrical shorts and ensure safety. The type of insulation required depends on the voltage and current rating of the motor power wires. For low voltage wires, up to 600 volts, heat shrink tubing or electrical tape may be sufficient. For high voltage wires, over 600 volts, insulated sleeves or compounds designed for high voltage applications are necessary. Following best practices is crucial. Locate splices in an accessible location within the control cabinet. Use splices that are rated for the wire size, voltage, and current load. Follow the manufacturer's instructions for proper splicing and insulation techniques. Protect splices from damage and environmental factors. Inspect and maintain splices regularly. Consulting the electrical codes and standards applicable to your jurisdiction for specific requirements regarding splicing motor power wires in the control cabinet is always recommended. When making electrical connections, it is crucial to consider the current carrying capacity of the conductors and the ampacity of the terminals. The National Electrical Code, or NEC, provides guidelines and tables for determining the appropriate wire size and termination methods for various applications. Using conductors and connectors that are not properly rated for the intended current can lead to overheating, insulation breakdown, and even electrical fires. In addition to current carrying capacity, voltage drop is another important factor to consider. Voltage drop occurs when the voltage at the load end of a circuit is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides recommendations for limiting voltage drop in branch circuits and feeders. When splicing or terminating conductors, it is essential to use approved methods and materials. Wire connectors should be listed by a recognized testing laboratory such as Underwriters Laboratories or UL, and should be suitable for the type and size of conductors being used. Proper tightening torque is also critical for ensuring a reliable connection. Over-tightening can damage the conductors or connectors, while under-tightening can lead to loose connections and arcing. The NEC specifies torque requirements for various types of connectors. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protective devices, such as circuit breakers or fuses, to trip and to energize the circuit. Bonding ensures that all metal parts of an electrical system are at the same potential, reducing the risk of electric shock. The NEC provides detailed requirements for grounding and bonding. In industrial settings, it is common to use shielded cables to protect sensitive electronic equipment from electromagnetic interference or EMI. Shielded cables have a conductive layer that surrounds the conductors and is connected to ground. The shield helps to block EMI from entering or leaving the cable. The NEC requires that the shield of a shielded cable be properly terminated to ground. When working with electrical equipment, it is essential to follow lockout/tagout procedures to prevent accidental energization. Lockout/tagout involves disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to indicate that the equipment is being worked on. Only authorized personnel should be allowed to remove the lock and tag. Regular inspections and maintenance are critical for ensuring the continued safe and reliable operation of electrical systems. Inspection should be performed by qualified personnel and should include visual checks for damage, loose connections, and overheating. Maintenance should include cleaning, tightening connections, and replacing worn or damaged components. It's always a good idea to consult with a qualified electrician or electrical engineer when dealing with complex electrical systems. They can help ensure that the system is designed, installed, and maintained in accordance with applicable codes and standards. It is crucial to select the correct type of wire for the specific application. Factors to consider include the voltage rating, temperature rating, and environmental conditions. For example, THHN wire is commonly used for general-purpose wiring in dry locations, while THWN wire is suitable for wet locations. XHHW wire has a higher temperature rating and is often used for high current applications. The size of the wire is also important. The NEC provides tables for determining the minimum wire size based on the ampacity of the circuit. Using undersized wire can lead to overheating and voltage drop. When pulling wire through conduit, it is essential to use a wire lubricant to reduce friction. This will make it easier to pull the wire and prevent damage to the insulation. The NEC specifies the maximum number of conductors that can be installed in a conduit of a given size. Overfilling a conduit can make it difficult to pull the wire and can also lead to overheating. When terminating wires at terminal blocks or other connection points, it is important to use the correct size and type of terminal. The terminal should be properly tightened to ensure a secure connection. Over-tightening can damage the terminal or the wire, while under-tightening can lead to loose connections and arcing. When working with electrical panels, it is essential to maintain proper clearances. The NEC specifies the minimum clearances that must be maintained around electrical panels to provide safe access for maintenance and repair. The electrical panel should be kept clean and free of obstructions. Dust, dirt, and debris can accumulate inside the panel and cause overheating or other problems. Regularly cleaning the panel with a vacuum cleaner or compressed air can help to prevent these problems. Surge protection is important for protecting sensitive electronic equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other events. Surge protective devices, or SPDs, can help to divert surge current away from the equipment. SPD should be installed at the service entrance and at branch circuits that feed sensitive equipment. Arc flash is a dangerous phenomenon that can occur when electrical equipment is energized. An arc flash is a type of electrical explosion that can produce intense heat, pressure, and light. Arc flash can cause serious burns, blindness, and even death. The NEC requires that electrical equipment be labeled with arc flash hazard information. This information includes the incident energy level, the working distance, and the required personal protective equipment, or PPE. When working on or near energized electrical equipment, it is essential to wear appropriate PPE. This may include flame-resistant clothing, gloves, eye protection, and a face shield. Proper training is also essential for working safely with electrical equipment. Employees should be trained on the hazards of electricity and the proper procedures for working safely. The Occupational Safety and Health Administration, or OSHA, has regulations that require employers to provide electrical safety training to their employees. Power quality refers to the characteristics of the electrical power supply, such as voltage, frequency, and waveform. Poor power quality can cause equipment to malfunction or operate inefficiently. Common power quality problems include voltage sags, voltage swells, harmonics, and transients. Power quality monitoring equipment can be used to identify and diagnose power quality problems. Power factor is a measure of how efficiently electrical power is being used. A low power factor indicates that a large portion of the current is being used to create magnetic fields rather than to do useful work. A low power factor can increase energy costs and reduce the capacity of the electrical system. Power factor correction equipment can be used to improve the power factor. Harmonics are sinusoidal voltages or currents that are multiples of the fundamental frequency of the electrical power supply. Harmonics can be caused by nonlinear loads such as electronic equipment and adjustable speed drives. Harmonics can cause overheating, equipment malfunction, and interference with communication systems. Harmonic filters can be used to reduce the level of harmonics in the electrical system. Uninterruptible power supplies, or UPSs provide backup power in the event of a power outage. UPS are commonly used to protect critical equipment, such as computers and servers. UPS can be either online or offline. Online UPS provide continuous power to the load, while offline UPS only switch to battery power when a power outage occurs. Standby generators provide backup power for larger facilities. Standby generators are typically powered by diesel or natural gas. Standby generators can be either automatic or manual. Automatic standby generators start automatically when a power outage occurs, while manual standby generators must be started manually. The NEC Article 700 covers emergency systems. These systems are intended to automatically supply illumination, power, or both to designated areas and equipment in the event of failure of the normal supply. Emergency systems are typically required in hospitals, fire stations, and other critical facilities. The NEC Article 701 covers legally required standby systems. These systems are intended to automatically supply power to selected loads in the event of failure of the normal supply. Legally required standby systems are typically required in nursing homes, sewage treatment plants, and other facilities where interruption of power could have serious consequences. The NEC Article 702 covers optional standby systems. These systems are intended to supply power to selected loads in the event of failure of the normal supply, but are not required by law. Optional standby systems are typically used in businesses and homes to provide backup power for lighting, appliances, and other equipment. When designing an electrical system, it is important to consider the future needs of the facility. The system should be designed to accommodate future growth and changes in technology. It is also important to consider the energy efficiency of the system. Energy-efficient equipment and practices can help to reduce energy costs and improve the sustainability of the facility. Regular maintenance and testing of electrical equipment are essential for ensuring its continued safe and reliable operation. Maintenance should include visual inspections, cleaning, and testing. Testing should be performed by qualified personnel using calibrated test equipment. Records of maintenance and testing should be kept for future reference. It's important to document any modifications or repairs made to the electrical system. This documentation should include a description of the work performed, the date of the work, and the name of the person who performed the work. Accurate documentation can be helpful for troubleshooting problems and for planning future work. Consulting with a qualified electrical engineer or electrician is crucial for ensuring that the electrical system is designed, installed, and maintained in accordance with applicable codes and standards.